Okay, we're recording. Um, okay, so section 5.3, I've decided I'm going to split it into two lectures. I haven't yet adjusted our schedule, but that'll come later on today or tomorrow, where I'll figure out what we're going to cut in order to allow us to expand this to two lectures, because there's just a lot here. Our topic is continuous functions on intervals. Okay, two really important theorems in here, and that's why I'm going to cut it in half. So we'll do one really important theorem today, another really important theorem Friday. Okay. Let's do some examples though first of just continuous functions on intervals. Let's just look at x squared. So we all know the graph of x squared, something like that. What we're going to do is we're going to look at the images of intervals under continuous functions. So I'm going to look at things like this, f of this interval. So I mean all the values that you get when you plug in the numbers from that interval into f. What do we get out with this function?
Zero to 4.
Thank you. 0 to 4, closed interval, right? What if we do, say, the open interval from -1 to 3? What do we get out?
Zero to 9, closed on the left, open on the right.
Thank you. Yeah, half open interval. Okay, and finally we could do infinite intervals. Remember, when I say infinite interval, I mean an interval of infinite length. Other than the trivial empty set and singleton intervals, all intervals have infinitely many points. They just have a finite length. Okay, so if we looked at the interval from -infinity to 7, what would we get out?
0 to infinity, closed on the 0.
Perfect. 0 to infinity. That's the whole range of f, right? Second example of 2. Let's look at 1 over x. There we go. Not allowed to define that at 0. Okay. Now, f of, let's say the interval 1 to 2.
One half to 1, closed.
Thank you. 1/2 to 1, closed. How about open from 0 to 1? Let's close it at 1.
Closed 1 to positive infinity.
1 to infinity. And I'll just do one more so we can have 3 of each. If we went 3 to infinity, open at 3, we'd be going 1/3 to, oh. What would we get?
1/3 to 0.
Yep, but it would go the other way, right?
Or 0 to 1, right?
Yeah.
And they both be open, right? Yeah.
Both be open. Okay, well there's 6 examples of continuous functions on intervals. Anyone want to make any conjectures about what we can say about continuous functions on intervals?
Yes, I would like to make a conjecture.
Go ahead.
The image of the interval is equal to an interval with bounds equal to the image of the original bounds. Or the limit of the bounds, I guess maybe is better. Because you can't plug infinity into x.
What are you gonna say about this example? Right. So there we're looking from here to there. And our bounds on our interval are coming from there.
This requires a little more thought. I'll have to get back to you.
But let's say, I'll spoil a little bit of the surprise here. We're going to talk about the bounds next lecture. So don't think about the bounds. What was the first half of your conjecture?
I thought I really only said about the bounds, didn't I?
No, you said something before that. I think. Anyone else with a conjecture? What seems to be true with all of these examples?
Daniel said that the image of an interval was another interval.
Yeah, the image of an interval is another interval. That's all we're going to prove today. Okay. Now, some of you might remember the name of this theorem from Calculus 1. Anyone remember it and want to volunteer? So, what am I trying to say? The way you would remember this, I think, this theorem is just this statement: the continuous image of an interval is another interval. Continuous image means, you take a continuous function, apply it to that interval, you get another interval. But the actual theorem statement, we want to be a little bit more precise here. So let's be a little bit more precise. Let I be an interval. And let's let F map from I to R be continuous. Now, when we just say continuous, what we mean is that you're continuous on your entire domain. Okay? I'll put that in parentheses so we remember, but okay. But because we've defined the domain of F to be just the interval I, when we say it's continuous, we mean it's continuous on I. Okay? Then our conclusion is that the image of I is also an interval. Okay? Anyone feel like volunteering the name of this theorem yet? Or are you still thinking of it? You've heard it. You've heard it. You just might not recognize the theorem in this form.
There's something in the chat.
Oh. Yeah, thank you, Matthew. That's it. This is another way to state the intermediate value theorem. or we're just going to call it IVT from now on. Okay? Now, in Calc 1, you did not see it written the way I've written it. Think about what if you remember the intermediate value theorem, what do you remember about it? It says, if a continuous function takes on a value, and then takes on another value, then in between it took on all the values in between. Right? So your picture for your intermediate value theorem is probably, in your head, your picture is probably something like there is f of a, and let's say here is f of b. Then if I pick any value in between those two, any value in between those two, let's say right there, then at some point our function took on that value. Okay. You'll notice it also, this example also took on values outside of that range. We're not saying that can't happen. It definitely can happen. But the only thing we're going to be able to guarantee is values between those two. Okay. And I think in the picture it's pretty clear why this is happening, right? The continuous function is not allowed to jump over that dotted line. Right? That's what continuity means, right? Except, technically speaking, that is not what continuity means. Continuity means this thing with epsilons and deltas. So we have to somehow convert the epsilon delta definition into this property. Okay. Any questions before we start the proof?
Yeah, I have a question.
Sure.
So just because we're mapping to an interval, I don't see how that guarantees that we get a value in between.
So remember that intervals satisfy the betweenness property.
Right. I get that, but I don't see why necessarily that I don't know how to explain it, but I don't exactly see how we guarantee that if we pick a point between the two that our interval contains that, or
Mm-hmm.
I know the betweenness property. I don't know how to explain it. Maybe I'll just figure it out looking at
So the interval of values contains f of a and f of b.
Mm-hmm. Oh, so it has to have the stuff in between it. Okay. I got it now. I was thinking that the interval could be placed in some weird spot, but I guess
Oh yeah,
it
so
doesn't matter.
this interval I should have drawn it over here on my picture, right? This interval I guess it's got to contain a and b. So let me write down this is how we're going to start the proof, is we're going to write down what we really want to show, okay? And when we write down what we really want to show, you'll see the intermediate value theorem as you remember it. Okay, there was another question?
Oh yeah, could I ask a quick question?
Of course.
This is technically a slightly stronger statement than the intermediate value theorem because, I mean, there could be values below f of a like you've shown there, and those would also be. And I was just wondering, is this equivalent or is this maybe a slightly stronger statement?
I can see how you would say it sounds stronger, but it's actually not. All we're going to show is the betweenness property. So the fact that the values take on these things outside that interval. But then if you go and you apply the intermediate value theorem to points down there, you'll get that you have you'll get that you have an interval.
Okay.
So think about it as soon as we write down what we're actually going to show here. Okay, so we need to show that the set of values, so that's the set f of I, satisfies the betweenness property. Okay, that's because we proved a theorem way back in lecture 7, actually. I was just looking at this. That said that you're an interval if and only if you satisfy the betweenness property. Okay. And in fact, you know, the next time I teach this course, I'm going to take that to be the definition of an interval. But we didn't do that. We proved a theorem that said that. Okay, so now to show we satisfy the betweenness property, let's take two values in f of I and a value in between. So suppose we have f of a, that's a value in f of I, and we have an f of c, it's a value in f of I, and then we have some real number in between them. And now our rules are that a and c have to be in the interval, and all u has to satisfy is it has to be a real number. Okay, so if we have that, we want to show that f of I satisfies the betweenness property, we've got to show that the number u lies in f of I, right? And to show that something lies in f of I, we have to show that it is the image of a point in I. Okay. So let's do that. We must find some point in our interval, and I'm going to call it B, so that f of B equals u.
Excuse me?
Yeah.
Shouldn't those be strictly less than signs? Because otherwise it would be trivial, right? We could just pick A or C to be B.
You're right. If we have equality, we're talking about these signs. You're right that if we have equality in one of those, then it's trivial, but that doesn't make it wrong,
Okay.
right?
Mm-hmm. Okay, that's fair enough.
And if you go back to the technical definition of betweenness, we did use a weak inequality there, so I wanted to use the same one here. Okay. Okay, so are we clear about the goal? Now, what we're actually going to show is that this number b that we need to find lies between a and c. That's a little bit stronger. Okay. So let's go find this b. Now, there's two proofs of this theorem. As far as I'm concerned, there's only two proofs of this theorem. Well, I'm sorry, I take that back. There's three proofs of this theorem. One uses machinery that we're not going to have until next semester, but it's really slick, really quick. It's a great proof, but we can't use it because we'd have to define compactness and connectedness and all this other stuff. The second one actually goes and tries to find this point B explicitly. Okay, that's the proof that your book gives, and I recommend you take a look at it. So your book says, okay, well, I'm going to divide the interval from A to B in half, right? And this point B is going to be in one of those two halves. So I'm going to focus on that half, and then I'm going to divide that in half. And you keep dividing this interval in half, and then you use this nested interval theorem. And that shows that when you nest those intervals like that, you eventually have a point in the intersection, and that one has to be your point B. Okay. I'm going to do the supremum proof. Okay, so in the supremum proof, we just go and we define a set, and then it's kind of clear that B has to be the supremum of that set, and we prove that it really is. Okay, so now I want you to think about how did we prove that that there's a real number. That the square root of 2 is a real number. We looked at the set of all real numbers whose squares are at most 2. And then we said it has a supremum, and then we said that supremum has to be the square root of 2. We're doing an analogous thing here. We're going to define B to be the set of X. Now, I'm going to add a little bit of a silly condition. It's the set of all real numbers X between A and C. The reason I'm writing it that way is that I haven't said if A is to the left of C or if C is to the left of A, and I don't want to say. Okay, so A and C are somewhere in the real line. I'm looking at the numbers in between them. Okay, such that f of x is less than or equal to u. My first claim is that B is not empty. Why is that true?
I have a quick question first.
Sure.
Is this between a strict or weak between?
Oh, sure. Let's go weakly between.
Okay, so it can take on A or C.
Yeah.
Okay, then I can answer the second one. Because either f of A or f of A is going to be less than
Or equal to.
u.
Yes. Yes, that's the correct answer. A is in the set B. Okay, because A lies weakly between A and C. And f of A is less than or equal to u by how we chose u. Okay? Now, we know that B is bounded. Why is B bounded?
Because it's a subset of our interval, which is bounded.
Yeah. A and C are bounds on B. One of them is a lower bound, the other is an upper bound. We're not saying which one is which, okay? But they're bounds. So B is bounded on both sides. So it has a supremum. Okay. Therefore, B has a supremum. So let's let little b be the supremum of B. Now, little b should be the point that maps to u. Okay, why should it be the point that maps to u? Because everything to the right of little b is greater than u, is mapping to things that are greater than u. And f is continuous, so it can't jump from something less than u to something greater than u. So we would think that at B, we have to be equal to U. Okay? But again, we have to use the epsilon delta definition of continuity. So, to do that, let's just see what happens if we use that definition with an arbitrary epsilon. So let epsilon be arbitrary. Okay. We get to pick epsilon, and we will pick it later. But for right now, just think epsilon is really small. Okay. Because f is continuous at B, there is some delta such that, and now this is just the thing in the definition of continuity, f of x is close to f of b whenever x is close to b. Okay. Let's draw a picture.
Dr. Bader,
Yeah.
so here we're talking about B, and we're claiming that it's the same B as above. Do we just keep the same symbol even though we haven't shown that they're the same yet?
Oh, okay. That's a subtle point.
Like, you know, let B prime equal the supremum of B, and then we'll show that B prime equals B or something like that.
Yeah, so you're referring to this sentence we used above?
Yeah.
So so that sentence that we used above was, that was wishful thinking, I would call it. It didn't actually define a B.
Okay.
You know, if we'd said there exists a B such that, then B would be defined.
Okay,
but
so
what
we're
really,
saying we want to find a
Yeah.
B. Here's a B that we thought up of.
yeah, and now we'll show it's the right B.
Okay.
Now we'll show it does what we wanted it to do.
And how do we show that this B is in the interval so that it's continuous?
B,
Is it because it's between A and C?
yeah.
Or,
Oh.
well, it might not be since it's the supremum.
That is a good question. When we say x weakly between A and C, we're talking about a closed interval. So little b could not be greater than the maximum of A and C.
Okay, because it's a closed interval, we know that B is in B.
Yeah.
Okay.
In this case, B is just either A or C, depending on which one is the actual upper bound of the set. So interval.
Little b is not necessarily A or C. It's only A or C in the kind of trivial case where U was f of A or U was f of C. Okay. Otherwise, it's going to be between them. You know.
Because we're taking a subset of this interval. We're not taking the whole interval.
Yeah.
Yeah, I have to think the set B.
It's at most A or C, or at least A or C, whichever one's which.
Mm-hmm. Okay, so here's a picture. What does the set S look like? We're not going to prove what the set S looks like, but if you think about it, oh, yeah, sorry. Let's not make any claims about what the set S looks like. That would be equivalent to the theorem we're trying to prove. Sorry. Let's just draw this picture. We know B is somewhere between A and C. I don't know which side A is on, and I don't know which side C is on. But they're on the outside. Okay? Now, let us go delta to either side of B. Now we're going to think about all function values in there as being close to f of b, okay, because they're all within epsilon. So what I'm going to write, all points here have their f values. So the best way I can figure out how to write that is f of them is within epsilon of f of b. Okay, close to f of b. Okay. Now, over to the right, what do we see? There are no points of S to the right of B, right? Because B is the supremum. So what can we say about every point to the right of B? Because it's not in S. Oh, sorry. I said S. I meant capital B. Because all these points are not in capital B, what can we say about them?
Their image is greater than you.
Mm-hmm. Everybody over there has an image under F that's greater than you. Now we go over to the left. What can we say in the left half of this? Well, we can say that there is a point of capital B. Okay? Why is there a point of capital B over there?
Professor, is that just like f of the point?
Mm-hmm.
Okay.
Yeah, F of that point is greater than you. Okay, so my claim over on the left is there's at least one point here in capital B. Why is that true?
Because since b is the supremum, it has to be greater than one of the other ones?
Yeah, so it's because little b is the supremum. And what that means is that b minus delta is not the supremum. Okay, so since b minus delta is not the supremum, there is a b prime that's bigger. That's in the set. Okay, so to the left, there's at least one point that lies in capital B. That means its function value is at most u. To the right, all the points have their function values greater than u. Okay? And because we're continuous, all of these function values are really close to our function value. And now we're just going to put that together and see what it says, okay? That was the picture. Picture is not part of the proof, but it informs the proof, which we now write. So I'm going to choose some B. I'm going to write B superscript minus because it's to the left. Okay, it's in the open interval from B minus delta to B, and it's in capital B. But that's not quite right. That needs to be, I need to allow the possibility that actually B minus could be B.
Wouldn't B minus automatically be in that interval? Automatically be in the set B if it's in that interval?
No. Because being in the set B means that your function value is less than or equal to u. And our function could be going up and down. You know, it could be oscillating. So there could be certainly be some points over there who are not in capital B because their function values are too big. Okay. Choose some little b over there, b minus over there, because b minus is in b. What do we know? F of b minus is at most u. It's part of being in capital B. But then we also know that it's within delta of b. So because it's close to b, that means that its function value is within epsilon of f of b. Remember, we just let epsilon be arbitrary. So this is really true for any epsilon. For any epsilon we pick, there's a delta so that we can do this. Okay. This means if we combine these two, what do we get? Well, I want to bound f of b. Okay. Because f of b minus and f of b are within epsilon of each other, the absolute largest that f of b could be, and actually this is a strict inequality, but f of b could not be larger than f of b minus plus epsilon. Okay, again, I'm using the fact that when we see one of these guys that really says that the two quantities in the absolute values are within epsilon of each other. So the largest that one could be is the other one plus epsilon. Okay? On the other hand, we know that from the first inequality, we know that f of b minus is at most u. So this is all at most u plus epsilon. Okay. Is this progress? Well, yeah. We showed that f of b is close to u. Right? Now let's go over to the right-hand side. So on the other side, for any point over there, b plus in this interval, what do we have? We have that f of that point is greater than u. Okay, because there's no points of capital B over there.
Professor?
Yeah.
Is this kind of another, you know, when you write the green line, does that mean we're like pausing the proof and we're doing like some more detail, like?
Oh, I'm sorry. No. For the green line, I'm just separating my thoughts.
Okay, got you.
So this is kind of a new thought. They would be, if I were writing this in a way that you could see, the green lines would be just paragraph breaks. Okay.
Right.
Okay, so we go look at any point over there on the right. Its function value is greater than u, but it's close to b. So its function value is close to f of b, right, within epsilon. And now, again, we combine these, but we want the other direction on f of b this time. F of b, the absolute smallest that f of b could be would be f of b plus minus epsilon. And f of b plus is greater than u. So we get u minus epsilon as a strict lower bound on f of b. what have we proved? No matter what epsilon we started with, because we let epsilon be arbitrary, we found that f of b was greater than u minus epsilon, and on the other hand, it was less than u plus epsilon. Now, how can that be true for every epsilon?
F of B is U.
Yeah, there's only one way that can be true. F of b has to be equal to u. And that is exactly what we wanted to prove, right?
Wait, Professor, I don't understand how on the right side it's not a weak inequality
Mm-hmm.
because it was a weak inequality when it was u plus epsilon.
Mm-hmm. That was a weak inequality, but there was already a strong inequality.
Oh, okay. Thank you.
Yeah, you know, that's always kind of a tricky thing. The strong inequality, in some sense, poisons the whole chain of inequalities, right? Whereas the weak one, yeah, no matter how many weak ones you throw in after a strong one, you're not going to make it weak again. But if you get a strong one, then it's always going to be strong. Okay, any other questions?
I have a quick question.
Yeah.
So how do we know that B plus it does actually exist? Like there actually is a point between B and B plus delta?
Because delta is positive.
Delta's positive.
Mm-hmm.
Okay.
Oh, and we're not talking about arbitrary domains here, in case that was your concern. Our function is defined on an interval. So we got all the points in there. Okay.
All right. Okay. So we're just assuming delta is sufficiently small that B plus delta is in that interval.
Yeah. Yeah. You're making me a little bit nervous about the. Yeah. I didn't handle the case where u equals f of a or u equals f of c like I should have. I needed to dispense with those cases at the beginning so that then I could say that we can assume that delta is sufficiently small, that b plus delta is less than c, and b minus delta is greater than a.
Okay.
Okay?
Mm-hmm.
So there was a better way to, there was a thing I needed to do that I didn't do. I'll fix it in the notes. I'm going to put notes on the canvas for this. Okay? Okay, so that's the supremum proof of the intermediate value theorem. Continuous function maps intervals to intervals. Okay. We're not saying anything about open, close. We're not saying anything about the bounds. Okay. We saw in our examples that stuff can get tricky. Okay. Tomorrow we're going to talk about the bounds. Not tomorrow, Friday we're going to talk about the bounds. Okay, with my last few minutes, let me just say, historically, before the definition of continuity was really formalized into the epsilon delta definition that we know now, some mathematicians took satisfying the intermediate value theorem as the definition of continuity. Okay, and it kind of makes sense, right? I mean, that's kind of capturing something about continuity, right? It's capturing that you can't jump over lines. but there's a problem. While every continuous function satisfies the IVT, there are nasty functions that are not continuous but still satisfy it. Oops. And I just want to talk about one. It's a great example to have in the back of our minds, and we haven't looked at it that carefully yet. So we look at this function that's defined to be sine of 1 over x as long as x isn't 0 and 0 otherwise. Okay, I'm going to go pretty quickly through this. There's more in your book too. What's going on with this guy? You could draw a much better picture of that, but that's kind of the idea. As we get close to 0, our periods just shrink rapidly, right? And then at 0, we've just kind of said, at 0, we're going to be 0. Okay? But here's fact 1. F of x is not continuous at 0. The easiest way I know how to establish that is to look at the sequential criteria for continuity. The sequential criteria would say if you've got a sequence of x values that converge to 0, then the sequence of function values of those have to converge to the function value at 0. So why is this not true? We can look at the sequence. Well, okay, we have. This is just a thing about sine. Sine of pi over 2 is 1. And then we add 2 pi. Sine of 5 pi over 2 is 1. And this goes on forever. So if we look at the sequence, 2 over pi, 5 pi, 2 over 5 pi, 2 over 9 pi, etc., that converges to 0, but now f of 2 over pi, f of 2 over 5 pi, f of 2 over 9 pi. So every one of those values is 1, so that converges to 1. Okay, and 1 is not equal to f of 0. You're good? So f is not continuous there. Now, I really do want to end this lecture on time, so I'm just going to say, why do we not satisfy, why do we satisfy the intermediate value theorem? So fact 2, this function satisfies the IVT. Okay. Consider an interval. We need to show every interval. We satisfy the IVT for every interval I. So if 0 is not in I, then f satisfies the IVT for I. Because, why?
Because it's continuous at all those points?
Mm-hmm. Because it's continuous on I. That follows from I think our previous lecture, where we did this is the composition of a continuous function with 1 over x, which is continuous at x not equal to 0. Okay? But if 0 is in I, then we still satisfy the IVT even though we're not continuous there, because well, here's one way to put it. No matter how small delta is, f of, if we just look at the values that f takes from minus delta to delta, it takes on all the values. No matter how close to 0 we shrink our interval, we're always going to be taking on all the values. Okay, so the IVT will hold because no matter what function value you would like to get out of the IVT, you're going to get it. Okay? So that is an example of a function that is not continuous and still satisfies the intermediate value theorem. What that means is that the converse of the IVT does not hold. Right? So satisfying the IVT is not a sufficient condition for being continuous. Okay. So that's the end of the lecture.